Hey everybody, welcome back. So, in this video, we're going to be talking about logarithmic functions. You might say, well, what's a logarithmic function? I'm about to tell you. Logarithms are a mathematician's way of undoing exponential functions, since we're very interested in doing these things, right? If we are given multiplication, we invent division. Addition, we invent subtraction, right? If we're given x squared, we invent the square root of x. We're very interested in being able to undo that which we do. And the most general context for that is known as an inverse function. And the idea for an inverse function is if I have a function f that takes some element x to some element y, I want my inverse function to take me back from y to x. And we're going to define a logarithm accordingly. So, here's our definition. Let a be greater than 0 with a not equal to 1. The logarithmic function with base a. So compared to the exponential function with base a, now we're going to have the logarithmic function with base a is f of x equal to log base a of x. I think your book uses base b instead of base a. Same thing, it's just a choice of letter. Is f of x equal to log base a of x defined by log base a of x is equal to y if and only if a to the y power is equal to x. So basically, log base a takes x to y if and only if, when you exponentiate, you would go from y back to x. And the bases match. Alright, so, in words, log base a of x is the exponent to which a must be raised to obtain x. And all of the properties of logarithms really center around the fact of it undoes exponential functions. So, the domain of log base a of x, or sorry, let's just put this under a proper heading. Logarithm properties. The domain of log base a of x is 0 to infinity, and the range of log base a of x is all real numbers. Both of these come from the fact that it's the inverse, which means instead of having domain r and range 0 to infinity, which would be the exponential function a to the x, instead it's going to have domain 0 to infinity and range r. Those swap when you talk about inverse functions. And furthermore, this is known as the inverse function property. Log base a of a to the x is equal to x for all x and r. So if you take a number, you take a to that power, and you take the logarithm base a, you get back the original thing. Please note, these a's do have to match. And also, similarly, a to the log base a of x power is equal to x for x greater than 0. Why x greater than 0? Because that's the domain of the natural logarithm, or the logarithm in general. Alright, let's do some other properties that we get from those. So, we're going to list some properties and we're going to prove them based off of the definition of logarithm function. For instance, log base a of 1, no matter a, is equal to 0. Since a to the 0th is always equal to 1. Another cool logarithm property. Also, log base a of a is equal to 1. Since a to the first power is equal to a. Right? So, because a to the 1 is equal to a, we get that the log base a of a is 1. Furthermore, log base a of a to the x is equal to x, as stated right here. Oh, I already stated that one. Never mind. Nothing new. It's already on this side of the board, so we'll just leave it there. Okay, let's do some examples. Log base 5 of 1 is 0. Log base 5 of 5 would be 1. Log base 7 of 1 would also be 0, right? Because again, even though the base is different, we're taking logarithm of 1, so it's 0. Log base 7 of 7 to the 4th power would be 4. That follows from this property right here. Log base 7 of 7 to the 4th is going to give us back that exponent, 4. And then additionally, maybe we have 12 to the log base 5. Or sorry, 12 to the log base 12 of 5 will be equal to 5. Why? Because we have the same base on the exponent and the logarithm. 12, 12, those match, which means that these cancel out and we're just left with 5. Alright, so that's the definition of a logarithm. Let's talk about a few of its other useful properties. First, how will you graph them? Well, you can make a table, and that would allow you to graph a logarithm, but tables kind of suck. Is there a faster way? Well, if you view the graph of a function as a set of pairs, x comma y, or rather, x comma f of x, the inverse function basically says, oh, swap those around. So f of x, aka your y value, x, is on the graph of f inverse. I don't recall if I've given you guys the notation for inverse functions yet, so I'm just going to say f inverse. Okay, what does that mean? It means to graph an inverse function, such as maybe, I don't know, log base a of x, reflect the original function which in the case of logarithms would be a to the x, across the line y equals x. And this has the effect of swapping all those pairs around, thereby giving you the proper graph. So for example, in the previous video we graphed 2 to the x. Let's copy that graph down again right here. Alright, so this is our original graph of 2 to the x power from the previous video. Now if we wanted to graph log base 2 of x, we'd say, okay, we're going to swap all the xy pairs. I see that I have the pair 0, 1, which means I'm going to have the pair 1, 0. I see that I have the pair 1, 2, which means I'm going to have the pair 2, 1. We have 2, 4, which means we're going to have 4, 2. We have negative 1, 1/2, meaning we're going to have 1/2, negative 1. We have negative 2, 1/4, meaning we're going to have the point 1/4, negative 2, and so on. Which means that the graph of a logarithm function is going to look roughly like this. So this would be log base 2 of x. And again, we're getting that by just flipping it across the line y equals x. Which looks a little weird because we have a scale of 2 right there and a scale of 1 on this axis. Don't worry about that. Just make sure everything fits nicely. But yeah, that would be our graph for log base 2 of x. And all other logarithm functions are going to be graphed similarly. They're all going to look something like that. And because we're only working with positive bases, we don't have to worry about something weird happening like that. Alright, where to go from here? Yes, some properties we can see about log base a of x based off of this graph and all their others. Log base a of x has an x-intercept at x equals 1, and the limit as x goes to 0 of log base a of x is technically negative infinity and approaches 0 from the right side. The left side limit doesn't actually exist. Alright, those are some key properties of logarithm. What are they good for? Well, let's see. Before we should talk about what they're good for, we should probably talk about a couple of pieces of notation. There's 2 logarithm bases that stand out above the rest, right? The base is at number a. There's 2 values for a that stand out above the rest. I would ask you for any guesses, but we're in a YouTube video. So, definition. The common logarithm is log base 10 of x, denoted log x. So when we're working with log base 10, we just say, okay, omit the little 10 from the subscript, right? A lot of important things are log base 10 scales. For instance, the Richter scale, measuring earthquakes, is a log base 10 scale, which is why if you have a 5.0 earthquake, by definition, we can write this as log base 10, or aka log, of 10 to the 5th, right? So the actual amount of energy in your 5.0 earthquake might be 10 to the 5th, I think joules or something like that. But if you have an 8.0 earthquake, it'd be the log of 10 to the 8th power, right? But 10 to the 8th is 10 cubed times 10 to the 5th. So 1,000 times 10 to the 5th. This is why, even though you see, 5.0 earthquake, 8.0 earthquake, I guess 8.0, that's pretty close to 5, right? Why are those two earthquakes so different? It's because an 8.0 earthquake has 1,000 times more energy than a 5.0 earthquake. So logarithms are good for representing large scalings in a very small, compact way. Alright, so that's the common logarithm scale, log base 10. And of course, the other important one, if we had an exponential function important enough, it was called the natural exponential function. It makes sense we're going to have a natural logarithm to balance it out. So, the natural logarithm is log base e of x, denoted ln of x for natural log. I think someone in French probably named it. It was like Logarithmic Functions or something. I don't know. I don't speak French. Alright, so these are the two most important ones. For mathematical contexts, this one is more important than that one. Natural logarithms also have a lot of more common applications in, say, physics and finance, right? Because if we're using exponential functions with e in finance, we're going to need logarithms with base e to undo. Okay, let's move forwards. Let's talk about some more properties that logarithms enjoy. Right, we have our exponential rules for working with exponential functions. How do those translate over into logarithm world? Alright. Let a be a number greater than 0 with a not equal to 1. Right, so now we can talk about log base a, since log base a is only defined for positive a with a not 1. Let's pick three numbers, x, y, and z in R, with specifically x greater than 0 and y greater than 0. Z can be anything, but x and y have to both be positive. Alright, well then, first logarithm law, log base a, so nomadic place, log base a of x times y is equal to log base a of x plus log base a of y. Multiplying within a logarithm splits up as adding the two logarithms. Division will similarly split as subtraction. So log base a of x divided by y is log base a of x minus log base a of y. That makes sense. And then finally, log base a of x x to the z is equal to z times log base a of x. An exponent pulls down in front, no matter what x is. We saw as an earlier property that this is true when x is a. Log base a of a to the z is just z, right? But it's going to be true no matter what our value for x is. Exponents will pull down and multiply in front. In my pre-calculus course, I proved these, but I think it's kind of a waste of time to do it for a calculus course. It's more important that you actually know them and say, okay, I understand what's going on. Just know these rules come from the properties of exponential functions and actually from the standard rules of manipulating those. All right, let's move forward then. We can use these to evaluate different expressions involving logarithms. Maybe we have log base 4 of 2 plus log base 4 of 32. Now, 2 and 32 are both not natural powers of 4. Right? I mean, you could view 2 as 4 to the 1/2, but 32 is going to be real weird, right? Our logarithm laws say, hey, this thing right here, log base a of x plus log base a of y, is the same as putting it together and multiplying. So it'll be log base 4 of 2 times 32. No, you're multiplying 2 and 32. You're not multiplying log 4 of 2 times log 4 of 32. It's log base 4 of 2 times 32. And there is a difference. All right. That's log base 4 of 64, which is actually 4 to the 3rd power by log number 3. It's equal to 3 times log base 4 of 4. Base matches what we're trying to evaluate, so that's just 1. This will be 3. All right. How about log base 3 of 189 minus log base 3 of 7. Now, neither one of these are powers of 3, so this would get, or actually no, 189 is, but 7 is not a power of 3, so this would get real nasty. 7 is prime. This is about as bad as logarithms can get in terms of if you were to try to expand this out as a decimal. But thankfully, our logarithm laws are here to save the day. Logarithm law 2 says this is equal to log base 3 of 189 divided by 7. And if you simplify that, it'd be log base 3 of 27, which is 3 cubed, so this whole thing is just 3. Finally, negative 1/4 to log base 2 of 16. You could view 16 as 2 to the 4th, or you could use our exponent law. For the sake of it, let's use that 3rd law. This is equal to log base 2 of 16 to the negative 1/4 power, aka 1 over the 4th root. Of 16. 4th root of 16 is 2. So this is log base 2 of 1 divided by 2. That's log base 2 of 2 to the negative 1st. So this all ends up being, by this law here, pulls down in front, negative 1 times log base 2 of 2, but log base 2 of 2 is just 1. There we go. All right, so they're helpful numerically, but they're also helpful with theoretical applications. So let's do a couple more logarithm evaluations, and then we'll see a real-world use. Let's see. We can save that for later. Let's one of the more theoretical uses would be, hey, we can solve equations involving logarithms and exponential functions now. Because they undo each other, just like multiplication and division. So if I told you, hey, solve maybe 5 to the, no, not that one, that one's too complicated. 3 to the 7x is equal to 3 to the 2x plus 1. All right, how do we do this? Well, we say, hey, I have these two things that match, and they're both exponential functions with the same base. It'd be really handy if I had an equation just talking about these exponents. So how do I get from exponential function to exponent? I take a logarithm with the proper base. So we'll note that log base 3 of 3 to the 7x is equal to log base 3 of 3 to the 2x plus 1. By the logarithm rules I recently erased, this here is 7x. And this side here is 2x plus 1. Oh, would you look at that? A linear equation that we know how to solve. Turns out, x is just one thing. This is going to be our general principle for trying to solve exponential equations. Is you're going to try to get it to be a place where you can take a logarithm on both sides, have that make sense to do, and then get just an equation involving the exponents, just variables, which are things we know how to solve. Let's do another example. Let's say we want to solve 2 to the 3x plus 4 is equal to 8. Again, we have an exponential function on this side. Maybe not great for us. How do we fix it? We'll take a logarithm. The logarithm we should choose, in this case, because we're working with a base 2 exponential function, we should choose the base 2 logarithm. So log base 2 of 2 to the 3x plus 4 is equal to log base 2 of 8. Alright? Well, logarithm laws say this side is 3x plus 4. This is log base 2 of 8. Turns out 8 is 2 cubed. So we get 3x plus 4 equal to log base 2 and the 2 cancel, so we're left with just 3. 3x is negative 1. X is negative 1/3. Excuse me. Alright, so that's all well and good. But even if this didn't simplify well, let's say this was like log base 2 of, I don't know, 27, some other number that didn't simplify well. That's okay. It's still just a number, and as long as we have just a number and an equation with just our variables, we can still get a numerical value for our desired quantity. It might not be a nice numerical value, but that's okay. The real world has messy numbers. Them's the breaks. Alright, we can also do the same thing with logarithms. So let's do that. Let's say we're told to solve log base 7 of x squared minus 1 is equal to log base 7 of x plus 4 plus log base 7 of x minus 2. Alright. So when we go to solve this, let me rewrite that a little bigger. When we go to solve this, we say, okay, what can I do? I don't really know what a to the log base a of x plus log base a of y is. I only know how to deal with one of these at a time. But thankfully, our logarithm laws say you can combine those. We have the addition of two logarithms with the same base, which means it's the same as the logarithm of the multiplication. So in other words, this is the same as log base 7 of x squared minus 1 is equal to log base 7 of x plus 4 times x minus 2. Or in other words, distributing that out, x squared plus 4x minus 2x minus 8. How do we go from here? Well, we have a logarithm base 7 on both sides. We don't like that. How do we undo it? We're going to use the exponential function with base 7. So we're going to note that 7 to the log base 7 of x squared minus 1 is equal to 7 to the log base 7 of x squared plus 2x minus 8. The 7 and the log base 7 cancel out, and we're just left with x squared minus 1 is equal to x squared plus 2x minus 8. Back in just normal variable world, where everything is nice, where we know how to work with things. Getting everything onto the proper side, let's see here, let's subtract the x squared on this side and let's add the 8 on that side. We get 7 is equal to 2x. So it turns out that x is just 7 divided by 2. Let's do another example. Yep. And then after this example, we'll see the real world application for all this. It's another compound interest thing, funnily enough. We're told solve 3 plus 2 times the natural log of 4x is equal to 12. Okay? How do we solve it? Well, I'm going to want to get the logarithm by itself because I know how to undo a logarithm by itself. I can undo it with an exponential function. All this other crap, this plus 3 and the times 2, I'm not sure how to deal with. So let's get rid of it by moving it to the other side. I'm going to start by subtracting 3, and we get that 2 times the natural log of 4x is equal to 12 minus 3 is 9. Okay? Divide both sides by 2. Gets you that the natural log of 4x is 9 halves. Great. Because now, even if I don't have anything else, I have a logarithm function by itself. And I know how to deal with those. We undo logarithms with exponential functions. Here I'm working with the natural log, log base e, so we're going to choose the natural exponential function. E to the natural log of 4x is equal to e to the 9 halves power. E and the ln cancel, we're left with 4x is equal to e to the 9 halves. Therefore, x is equal to e to the 9 halves, all divided by 4. A nasty number to be sure, but one that we got to pretty easily. It still works out nicely thanks to the logarithm laws. Alright, let's do a real world application. Broken even before it comes out of the box. Ridiculous. Both of these are broken. Slightly less so though, so they're still usable. Alright. Let's recall our compound interest formulas. Right, we have the discrete compound interest formula, which says A of t equals p times 1 plus r over n to the nt. And even though this is a complicated exponential function, it's still just an exponential function. And we have the continuous one, A of t is equal to p times e to the rt. So a nice simple exponential function. Now, this tells us, hey, by using logarithms, we can solve for specific values of p if we're given a. So that could be of interest to us, right? So let's ask the question. Suppose $2,000 is invested at 10% per year. Find the amount of time required for the money to double. If the interest is compounded at two different rates. Let's do one discrete rate and let's do one continuous rate. Why not? Let's say it's compounded quarterly. And let's say it's compounded continuously. Sorry, did I put n? This should be m. At least with the notation we've used, it's all the same. So in both cases, we're going to be left with an exponential equation to solve. So, we're going to be solving A of t is equal to, okay, I want my money to have doubled. Which means I'm going to be solving for when A of t is 2 times my original principal. Which in this case is $2,000. And we're solving for t, right? We're trying to ask how long would it take? Well, for part A, $4,000 is equal to, okay, we're talking about quarterly compounding, which is we're working with this first one. So it's equal to $2,000 times 1 plus interest rate is 10%. So 0.1, compounded 4 times per year. 4t. Why t? Because again, that's what we're trying to solve for. We don't know how long it's taking. We're trying to figure that out. How do we solve this? Well, this is an exponential function, so I should probably take a logarithm. I should probably not have this 2,000 here because it'll mess things up. So let's divide both sides by 2,000. We get 2. The dollar signs cancel out. How about that? 2 is equal to 1.025. Just making it in decimal. Why not? To the 4t. Now, we have a couple of choices here, right? We could take a logarithm with any base we want. So we could take a logarithm with a nice base and get a nastier number, or we could take a logarithm with a nasty base and get a relatively simpler number. Doesn't matter to me, but well, let's do it both ways. Option 1, we could say, okay, let's take a logarithm that we know of. Natural log is a really nice logarithm. Natural log of 2 is equal to the natural log of 1.025 to the 4t. Alright? Well, this natural log on this side, by our logarithm law saying exponents pull in front, becomes 4t times the natural log of 1.025. Okay, to solve for t, I'll just divide by 4 and this thing. So natural log of 2 divided by 4 natural log of 1.025 is equal to. So, this is one option. We work with a nice base, and we get a relatively complicated number, but natural log of 2 and natural log of 1.025 are pretty well done. Second option, let's go down here, just so we have room. We'll take a nasty base, and we'll say, oh, log base 1.025 of 2 is log base 1.025 of that thing. Okay, then we're left with log base 1.025 of 2 is equal to, because we took the proper base on this side, for this to cancel out, 1.025, 1.025, we're left with just 4t. So now you divide by 4, right? And you would get log base 1.025 of 2, all divided by 4 is equal to. Please note, this is not 2 over 4, this is this logarithm divided by 4. And both of those are valid answers. That's an interesting thing. Expressing the same number 2 ways can happen if we have 2 different logarithmic bases. So that's slick. Let's do part B. Right, if we want to compound continuously. So I'll let you guys erase this, or copy it down real fast before I erase. All right. For B, we get to work with the simple formula. So now we're just solving $4,000 is equal to $2,000 times e to the 0.1 t. Okay, well again, let's divide both sides by $2,000, get that out of the way. We're left with 2 is equal to e to the 0.1 t. And now we're working base e. There's only really one base that makes sense to choose, and it's the natural logarithm. We get that the natural log of 2 is equal to the natural log of e to the 0.1 t. This side just becomes 0.1 t. Let's divide both sides by 0.1, which is the same as multiplying by 10. We get 10 times the natural log of 2 is equal c. So, different amount of time if we compound quarterly versus continuously. And if you care about the decimal number for this, great, plug it into your calculator. It'll give you a decimal number. That's what they're for. All right, let's do another quick real-world application. And I'm going to make this one up off the top of my head, so who knows if the numbers will be nice, but it'll be cool. Hopefully. No promises. I know most people don't think math is cool. But for those of us nerds out there, here goes nothing. Suppose you are told an account with a 5% nominal interest rate compounded, let's say, semi-annually, has $10,000 in it. After 3 years. So you're told the present status of the account, you're told how long it took to get there, you're told the interest rate and the compounding. The question is, okay, how much should we start with, right? That's kind of the missing piece in this, is how much did the account have to begin? In other words, what was the initial principal? Your book has this again in the compound interest section. They give you a whole new formula for it. But you don't really need the whole new formula. Just work with the one for compound interest and it rearranges very, very swiftly. So, what are we told in this situation? We're told $10,000, the amount in the account is equal to the principal, thing we do not know, times 1 plus 0.05 divided by 2 to the 2 times 6. Now, heck, you don't even really need logarithms. Sorry, 2 times 3. You don't even really need logarithms to solve it in this case. Yeah, you don't even need logarithms to solve it. Okay, cool. You could use logarithms if you said, oh, it's compounded after t years or something like that. Yeah, let's do that. Why not? Game changer. Instead of 3 years, it's now t years. And we're still asking the same question. What is that initial principal? Okay, well, let's figure it out. Simplifying this ever so slightly, we get that $10,000 is equal to P times 1.025 to the 2t. So we're trying to find P in terms of t, because we're trying to find principal, right? And then we can say, oh, if we knew that this was the case after 3 years, we could plug in 3 for t, and we could solve that. Well, if I just divide both sides by p, we get that $10,000 over p is equal to 1.025 to the 2t. Let's take the nasty base logarithm in this case just to make everything simpler. That tells us log base 1.025 of 10,000 over p is equal to, okay, it's going to cancel with that on the side 2t. But we're trying to get p by itself. Now it's all in this logarithm. What do? Logarithm rules say division splits up as subtraction. So this is just log base 1.025 of $10,000 some number minus log base 1.025 of p is equal to 2t. So if we just divide everything by 2, we get t. We're trying to rearrange to get p in terms of t, so let's do it. We'd add this on both sides and subtract t. So we have 1/2 times log base 1.025 of 10,000 minus t is equal to 1/2 log base 1.025 of p. All right. Well, let's get p in there. Multiplying everything by 2 gives you log base 1.025 of 10,000 is equal to, or sorry, minus 2t is equal to log base 1.025 of p. And then you would exponentiate with respect to 1.025 on both sides. That's just a number, but we could also use, if you wanted, your logarithm laws, and you would get, or sorry, not your logarithm laws, your exponent laws, 1.05 times logarithm divided by 1.025, so the 2t is equal to p. That cancels out, and you get $10,000 divided by 1.025 to the 2t equals p. Which I guess you could have just divided by over there and skipped all of that. But then we wouldn't have had such a fancy exploration. So, that's kind of the cool thing, right? We ended up with a result that we could have gotten much more quickly, but we didn't know that we were going to get to this. We didn't know that was going to be a nice formula, unless you were smarter than me and you were yelling at me the whole time, just divide it! If so, props to you. I didn't think to do that. But that's the great thing about logarithms and exponential functions. As long as you keep working with them, as long as you make sure to obey the laws correctly at every step, it all works out at the end. And now if I told you, hey, t is 3, you know that it had $10,000 in it after 3 years. You would say, okay, I'm going to plug it in. I get 1.025 to the 6th power. That's just a number. Number over number is my new number. Simple. All right, I think that's all for this video. Have a great rest of your day.